I did update all the, I forgot to do 4 rounds, of course, but I just today updated all the YouTube stuff too. Okay, so before we can really do any physics, we're gonna, and we're gonna start soon talking about mechanics. We're gonna talk about dynamics and statics, and we're gonna look at forces and the actions, the effects of forces acting on objects, and start to get into some physics. But before we can do any of that stuff, we have to know how to describe motion very precisely in a way that we can all understand, and that there's a little bit to that. It's complicated by the fact that we live in a three-dimensional universe, and so we're going to start off really simple today. I don't know how far we'll even get today, but I'd like to get to just the point where we can talk a little bit about motion in one dimension. And honestly, motion in one dimension, it seems like it's really oversimplifying things, but it's not. Because really all we do with 3 dimensions, or more than 3 dimensions, if we want to talk about motion, is we just take that one dimension and we're just going to expand our discussion from one dimension into 3 separate dimensions that we're going to learn to separate and isolate, work with them independently. And so really, even though we work in multiple dimensions, a lot of the math that we do, we're able to simplify down to the point where we can still treat it as motion in one dimension at a time. Like for example, the x-axis. If I were to draw, and I'm sure you've seen this before, but I'll just throw it up here real quick. You've seen stuff like this. Motion in one dimension is pretty boring. Motion in one dimension, we would say, we'll just call that the x-axis, right? 2 dimensions, what axis do we add? We add the y-axis, okay? And we'll talk more about this later, but what has to be true about those 2 axes for this 2-dimensional space to make sense? They have to be perpendicular. Yeah, they have to be perpendicular. Okay, and now it gets a little trickier for an artistically challenged person like myself. But what is the 3rd axis that we would add if we want to? Okay, we got to add the z-axis. Good. So I'm going to draw the z-axis coming out of the board. And this is a little tough to do. And then it's going to go into the board, behind the board like so. Now, once again, if this is going to make sense as a coordinate system for us, and we'll talk a lot more about this in your math classes. We'll talk about this in calculus a lot. You'll talk about this in really all your math classes. You'll touch on this. What has to be true about all 3 of these? They have to be mutually perpendicular. It's a word we use in math that doesn't even show up in this rinky-dink textbook, but I want you to see it because you'll see it in your math classes and you'll see it in the future in college too. Orthogonal. Orthogonal, all that means if you have a mutually orthogonal coordinate system, it just means that all of the coordinate directions have to be perpendicular to each of the others, right? So in this case, if I were to try to draw this, I would, in 3 dimensions, I'd get something like that, which shows that the y and the z axes are perpendicular. We already know that the x and the y are, and then x and z are also, right? Okay? So in our universe, how many mutually orthogonal axes fit? 3. Okay. Does it have to be that way? No. In our universe it does. But in other universes it might be very different. In other universes it's possible, and we'll talk about this at some point about multiverse theory, kind of on a Friday thing. We have a little chance to just talk about some weird stuff. Modern multiverse theory suggests that there are lots of universes embedded in a multiverse, and that these other universes could very easily have much, much different makeups than ours. For example, they might have, and this is a little strange, we'll talk more about this later, but there might be 4 orthogonal dimensions that fit. Now we can't imagine what that would look like, but there might be, if the universe were different, there might be an obvious place for another axis to fit that would still be perpendicular to all 3 of the others. Okay? And they might even have weird things like maybe more than one time dimension, weird stuff like that. But anyway, I digress. So this is what our 3-dimensional coordinate system would look like. And ultimately, what we're going to be able to do is we're going to be able to take things like forces, which we'll learn to represent with vectors, and we'll maybe even say that word today and talk about what it means. And we'll be able to break up these forces and these other physical quantities into pieces that fit nicely into each of these separate directions of the coordinate axes. So even the stuff we're talking about today, albeit pretty simple, it's pretty useful. A lot of the stuff we'll do will not be that very different from it. Okay? So start things off, describing motion. Motion it's complicated by the fact that it's really difficult to draw a picture that represents motion, right? It's easy to draw pictures of static stuff, but things that are changing, it makes it harder, right? Because really what we do in physics, when we talk about changes in a system in physics, and we want to be able to model those changes and maybe understand them mathematically and make predictions, really a lot of times what we're doing is we're trying to link events in space-time. That means, like, if I snap my fingers right here, you can see that right there, where I have my fingers, is a place that we could all point to and agree on, right? But the time part is a little stranger. I mean, now it's gone. We've already passed it, right? But if we had a clock in here, or if we were running a movie, maybe, if we were just videotaping the class, well, we could run the video back, and at a certain frame, I would be snapping my fingers right here, and that constitutes what we call an event in physics, right? So it happens there, but then maybe I move my hand down here, and I snap again down here. Those are two different events that happen in different places, but also in different times, right? And motion is one way that we can link those things together. Maybe my hand is moving at constant velocity from there to there, right? And so we could use some equations that we'll soon learn that would allow us to predict how long it takes maybe to get there, stuff like that, right? But the point being, because time is involved, it's really difficult to represent this stuff visually. Now the book does something kind of interesting here. Does this make sense? I could do this. Like that. All right. So, I mean, what could you do? Does these pictures give you, I mean, how could you represent, how is motion represented there? It is blurred, right? That works, right? The ground is not blurred because it's not moving. Presumably the shutter took a little while to open and close, and so in the time it took to expose that picture, the car moved a little bit. And so that gives us a sense that the car is moving. I don't know if it's the greatest model, but how could you tell if something were moving faster as compared to slower? It's going to get blurrier, right? It's going to get more stretched out, okay? Same kind of thing here. Evidently, this picture is not available on CD. So it makes me wonder what that picture was. I don't know. Curious that way. How about something like this, right? We could demonstrate maybe frames in a movie like we talked about. Yeah, it is. Right? So we're just taking discrete pictures in time, and how would we tell where this person were running maybe the fastest then? Well, okay, maybe how angled they were if we want to get, but the distance between frames. Okay, distance between frames, displacement between frames, right? The further she travels between frames, presumably the faster she was moving because the frames are all being regularly created, right? Okay, assuming that, right? But let's assume that. We could maybe even superimpose those all in one frame and get an idea, right? So she seems to be moving at constant speed, it looks like, right? Same distance away virtually, and pretty close. Okay? So those are all reasonable ways to do this. What about something like that? Right? So these are, I think in our book they call these things motion diagrams. I had never seen these before, so obviously we're not going to spend a lot of time with them. The first time I'd ever even seen them, but they work. So can you see that in this case right here, this would represent constant speed, right? As compared to speeding up, right? And what's maybe our 10-cent word for speeding up? Acceleration, okay. And then what about right here? Okay, slowing down or deceleration. Deceleration is I understand where that's coming from. I'll just tell you right now that for reasons that will soon be clear to you, deceleration is kind of a four-letter word in physics. It's one that we don't like to use very much. And you'll see why today. I hope people get that far.
Is that because in order to decelerate, you need one force to act on it?
Well, not exactly. What do you think? Okay. So let's talk about this a little bit. And here's just maybe a simpler representation of the same stuff. This is kind of where I wanted to end with the motion pictures. I like this better in a way because in physics we like to simplify things. Right? The last picture was maybe, it was a little more artsy. We had pictures of, stick figures and they were people. But in physics we'd like to kind of remove sort of the personality from the pictures in a way and just make them as simply representative as possible. So and we'll do this. Later on, we'll create in the class when we're doing more stuff with dynamics and forces, and we'll create what's called a free body diagram, where we'll take maybe some complicated situation where we're throwing a football down the field, and when we draw the free body diagram to represent the forces acting on it, we're just going to draw the football as a point, right? Because we want to make the point is going to simplify the whole process a little bit, right? So this really is pretty good. This is constant motion. This is accelerated motion, right? Speeding up, and this is slowing down, or we might say decelerated motion, right? Okay, so let's look at how we can talk about some of these specific quantities a little bit better. Well, let's start off with, we talked about a coordinate system. Let's talk about vectors. Okay, have you heard the word vector before? Okay, raise your hand if you've heard the word vector and maybe dealt with vectors. Okay. So what's the definition of a vector? Remember? Okay, it could represent distance traveled. Sure. Represent.
We have to bring down trade here for the test.
Okay. Okay. So it was kind of. Gotcha. Okay. So
with the direction.
There are with the direction.
The forces.
And there's two parts here. Let's write this stuff down. This sounds like maybe we need to at least review this just a little bit. Okay, there are two kinds of quantities that we deal with in physics. Scalar and vector. Okay, scalar quantities, remember what they are? Could be speed. When it doesn't have a direction. When all it takes is a number. Okay, all it takes is a number to describe the entire quantity. So the number, and the word we use for number is magnitude. So it's only got one thing. Magnitude. Okay. Scalar. Those are both A's. Yeah. Scalar. So scalar has only magnitude, and you already told me that a vector has direction. It has magnitude and direction. In fact, it's got two parts. It's got a number part. It's got a magnitude and a direction. Give me an example of a scalar quantity. Speed. Yeah, it makes sense. If I say, hey, how fast are you going? You say you're in a car. If you're on the Bluetooth, I'm not talking about cell phone, you're on the Bluetooth, and you say I'm going 60 miles an hour. That's all I need to know, right? That's that single number with a unit attached, sure, but the number is sufficient. That gives me the speed, okay? These scalars are easy. You come up with lots. What's another one? Say it again. Okay, height. Yeah, how tall are you? 6'2". Is that about right? Yeah. Okay, good. Weight. Sure. These are all things. All it takes, we'll attach units to them, but all it takes is just a number, right? That's all we're asking for. And what page you on in your book? That's a scalar. How temperature in the room, right? Lots of things like that. It's a little tougher to find a vector. Vectors in physics, we're going to primarily use vectors, but you maybe don't talk about them so much in everyday life. What's a vector quantity?
Velocity.
Okay, velocity. Yeah, let's write down some vector quantities. So, examples of both of these. So you already told me scalar. We had, for example, we had speed, right? We had height. How about if we just say distance of any kind, right? That distance might be measuring a height. It might be measuring, some distance along the ground, etc. Corresponding to speed, though, the vector version of speed is called velocity. Give me an example of a velocity.
Like, we're going from east to.
Yeah, okay, I could say 60 miles an hour due east, and that's telling me a velocity, right? It's got to have some directionality associated with it. What do you suppose might be a vector equivalent of distance?
Like, 5 feet tall.
Well, I still say that's a scalar, right? Yeah.
Be like 20 miles north.
Okay, yeah. Okay, and I'm going to call that a position.
Is that a technical term?
It is. That is a technical term. Yeah. Position describes the physical location of a place, right? It's not enough. Like for example, if I say, "Where are you right now?" If you say, "Well, I'm
20 miles away.
yeah," even if you just say I'm 20 miles away. 20 miles away. That's not. What's that mean? 20 miles away. I mean, you could be any direct. You could be up in the air. I mean, you could be an infinite number of places and be 20 miles away. If I want to know where your position is, you could say I'm 20 miles due north of you, and then that makes sense, right? And that tells us a precise place, right? So position has to have both a magnitude, how far away, and a direction, right? Okay.
There's a, sorry,
Uh-huh.
if you're 20, say 20 miles away, there's a finite number of places you can be technically, correct?
No.
I think there's, would there be an
Well, it's
infinite?
like, sure,
infinite
be like
number?
a circle, and there's a finite.
How many points are there on a circle?
Infinite.
Okay.
But
no,
in,
so
but in
it
the
would
physical
be-
world,
yeah.
but in the physical world.
No, you could be,
No, because it could be like.
you could be literally.
Okay, I could be
half
here
step
or I
and
could be
quarter step.
there.
There, yeah, like,
Right.
it's 20 miles,
Okay.
20 miles, right?
Yeah, I'm not ignorant, I'll find it.
And it's a sphere.
Okay, so acceleration we kind of use in both ways, right? If I said, let's say I want to know what's your acceleration in the car. Well, maybe I just, it's not, unless I'm specific, maybe I just want to know what's your rate of change of speed. So if you say, yeah, I mean, but it's, fast is not an adjective that actually describes acceleration. It's quick, right? I don't even know if
Rapid.
it's hard to find an adjective that describes acceleration, because fast would really describe what up here? Speed or velocity, right? But not necessarily acceleration, right?
Extreme.
You could accelerate really at a really high rate for an extremely short period of time, and you may not change your speed that much, right?
That's why
Right.
you burn your tires.
Okay. Yeah. Okay. So acceleration really, I mean, they would be implied maybe by the context if we want to know a vector or a scalar. All right. So let's talk about some of these quantities then. Let's define. We're going to talk about one-dimensional kinematics, and the one dimension that I'm going to move in up here at the front of the room. I'm just going to walk in a line, just forward and backward. That's it. Okay. So my position is going to be measured relative to, we'll call this 0. This is the starting line, right? So I'm taking 1 meter steps. So what's my position right now?
2 meters.
Positive 2, right? Why is it positive 2?
Because you went
From your origin to.
Okay, I went in the positive x direction, right?
Oh,
So we'll define that as the positive x direction. I should have said that. We're assuming we're on the x-axis, let's say. Okay, so if I,
That was your origin.
so then what's my position right now? Well, say I took 2 steps, so negative 2 meters, right? Okay, yeah, well. Now, they're different places and they have different positions. My distance away from the starting line in both cases is just 2 meters, right? Because distance is a scalar. Scalars are always positive, okay? Does that make sense? I mean, it's distance, how far did you run today? I ran 6 miles. It says nothing about directionality. It just tells me the distance that I traveled, right? How far did I travel in a line across the ground, right? Okay, what do you think then if we want to define, how about, I bet you know this, average velocity. How do you think we define average velocity? What do you think? I mean, you've talked, I bet you've done enough, going back to your days in physical science and what do you think? It's close, close.
Should we take the average speed and the average angle of direction
Okay, so what Scott's factoring in here is he's factoring in that there has to be some direction associated with this. Okay, we can make it simpler than that. All it is, if we define my position in one dimension is just my distance along the x-axis from the origin, right? That's position, right? We're going to say that position in our book, I can't remember, our book does something dorky with this. I've read enough other physics over the summer that I can't remember which one ours does. I think ours uses D, which I don't like.
Change it.
Most books, yeah, it does. Most books would let position be denoted by an S. So when you go to college, be ready for that. It'll typically be an S and not a D. But because what's that? Yeah, that's fine, I don't care. And we're gonna be moving on the x-axis, so we could even just call it X if we want, right? So for us, position is equal to, we'll call it X. We'll even put an X of t, so maybe we'll even put a function of time in there if we want to. To make this a vector, I'm gonna put this little vector hat on top of it. Okay, in our book, it just makes it a bold letter as a vector. And some books do that. But it's hard for me to draw something bold up here. So when I want to make something a vector, I'm going to put this little symbol, vector hat, on top of it. Looks like an arrow with just, kind of half an arrow. Okay? So what do you think average velocity is then in terms of my position?
So well, if it has a direction, it's not distance, right? Because it's a vector font. So, can't remember, it starts with a D also, but it's another distance.
Displacement?
Yeah.
Ah, okay. Yeah. Velocity is technically displacement over time. But what do you think displacement is? So,
Basically the same thing as distance.
not quite, almost. Let's say I start, displacement is change in position. That's how it's defined. So let's say I start at -2 meters. That's my initial position when I start. And sometime later, I'm out here at +3 meters. What's my displacement? +5, because I started at -2 and ended at +3. Okay, let's say I start at +3 and I end at +1. What's my displacement? -2, because the displacement points in the negative direction, right? It's always my final value minus my initial value. So 1 minus 3 is -2. The negative has meaning though, because that's the negative direction, that's the positive x direction, right? Everybody get it? Okay, so we know that we'll add something here. Position is x. We'll say displacement equals delta x. What does delta mean in math? Change in. Delta, it just literally just means change in. Every time you see a delta, it means change in whatever follows it. So change in x. Okay. Another way of writing that would even be something like, we could say displacement might be x2 minus x1, something like that. Subscripts just mean this is my initial, my first position, and that's my second position. And the difference between those two is my displacement. A better way to do that, and once again, I just want to make sure I'm sort of staying on track with this textbook. Okay, they do this, good. Rather than my initial position being sub 1, what else do you think I could call it that might even be better as a subscript? Keeping in mind that position is going to be a function of time. So we're always thinking about a movie rolling forward. Well, we're going to start the movie when we start our stopwatch at time 0, right? We start the stopwatch at 0 and then something happens, right? I'm going to walk in the front of the room up here somewhere. So usually we'd rather denote our initial position with a sub 0. Okay? And a lot of times physicists, they would say that's x naught. Naught is like an English way of saying 0. And so you always just follow something with naught, it means that's our initial value. Maybe we'll give that a 1. Okay? So average velocity then is really just equal to change in position over change in time. So in our book, generally speaking, we're going to say delta D over delta T. But because we're on a straight line that's the x-axis, for our purposes today, we could even just say change in x when we're changing time. And one other thing, and I don't want to get you too bogged down with the symbols, and we won't even be that consistent with this maybe, but if I want to denote an average quantity, usually that means we put a bar over it in physics. So if we said something like V bar, it means average velocity. Okay. But the book doesn't do that. I just want you to see this stuff so you'll get an idea. For us today, all we're going to talk about is average velocity. We're going to have to compare that to instantaneous velocity. We don't really get to that for a while anyway. So for now, when we say velocity, we really just mean average velocity. Okay, so let's calculate a velocity then. Let's say that I'm going to start at -1, and I'm going to, here's the story. Start our stopwatch, and 3 seconds later, I'm out here at +5. Started at -1, 3 seconds later, I'm at +5 meters. What was my average velocity? How'd you get it? Okay, and we got the 6 because 5 minus -1, right? That makes sense? Going from -1 to 5 is positive, so displacement is 6 meters, divided by, I said 2? So divided by 3 seconds is 2 meters per second, right? Make sense? Okay, what if I did this one? What if I start at 0, and let's say I'm going to walk out, in 4 seconds I walk out to +2, and then I walk back to 0. Okay, what's my average velocity? 1. Seems like, why do you say 1?
Because you said it took you 4 seconds and you walked to 2 and walked out, so 2 plus 2 is 4.
Is 1. Okay. That's my average speed. Okay. What's my average velocity? 0. How come?
Because you're in position.
I'm ending at the same place I started, right? And so my total displacement is actually 0. So my average velocity was 0 because, in effect, I didn't go anywhere, right? Now, how is speed different then? Because that was right. That was average speed. What must average speed mean instead of average velocity is displacement over time? What do you think average speed would equal? Yeah, the distance I walked over time, right? And both of those are meaningful. If I want to know how many calories I burned, I probably want to take into account my average speed. But if I want to make a prediction of where I'm going to end up if I do that again, my average velocity would be more useful, right? Make sense? Okay. What's my average velocity what if I start at +1 and I walk out to +6.5 and then I walk back to -1 and it takes me 4 seconds to do that? What's my average velocity? I heard 1/2, is that right? How come negative? Yeah. Okay, so my displacement was my net displacement. It doesn't really matter what I did in between the start and the end, but I started at +1 and I ended at -1, right? So my displacement is -2 meters in 4 seconds works out to be what? -1/2 meter per second. Okay, why might that also be useful? How could I change the story and simplify it so I could end up starting at the same place and ending at the same place? Don't walk out there and walk back. I just walk slower. In fact, how fast do I walk? 1/2 meter per second in the negative direction for 2 seconds, or 4 seconds, right? Does that make sense? So when we talk about average velocity, we're just taking the simplest version of the trick that we just took, right? Make sense? All right, that gets us started.